All right, welcome everyone. Thank you for joining us. So before we get into who we are and what we're about, we're going to present to you our library, the EDA Toolkit. The EDA Toolkit, we only have 25 minutes, so we'll try to make this a little bit of a marriage between a demo and a tutorial. So the EDA Toolkit came out of a simple need. We didn't see a comprehensive all-in-one EDA library in Python, especially one that could handle both tables and visuals the way that we needed it to. So we built it ourselves. We combined the most useful functions that we've been using across our projects into one cohesive toolkit. So every project, as I'm sure you know, whether it's research, healthcare, business analytics, and the sort, starts with the same challenge: getting a reliable overview of the data before modeling. And the EDA Toolkit makes that step simple and consistent, so it gives you ready-to-share results that fit right into your workflow. So let's start by introducing ourselves, sort of. On the left, that's me, Leon Shpaner. Let's see here. On the right, it's my colleague, Oscar Gill. Oscar, introduce yourself.
Hi everyone, Oscar Gill, data scientist, UC Riverside.
I'm a data scientist with UCLA Health. So in the middle, that's our honorary co-author and debugging companion, the gray alien. We figured every project needs at least one extraterrestrial reviewer, but really this slide captures kind of who we are, what we're all about. We're a little bit playful, a little bit technical, and truly command line powered. So everything you'll see today, figures, tables, everything you'll see visually can be generated straight from Python. There's no manual edits or anything like that. So for this presentation, we're using the adult income dataset from the UCI machine learning repository. This is a classic dataset based on the 1994 US Census data. It has about 49,000 records and 14 features. The goal is to predict whether someone earns more or less than 50K a year based on demographic and employment factors, but for this tutorial, we're focusing only on exploratory data analysis, not predictive modeling. All right, now that we've seen our data set, let's kick things off with Generate Table 1. Maybe you need this for a baseline summary, a reproducible report, or just to get a feel for your data before diving deeper. This is the tool that sets the tone for the whole toolkit. Think of it as your one-stop summary. You run a single line of code and instantly you get this clean, powerful breakdown of both continuous and categorical variables. So here we're using Generate Table 1. This function quickly summarizes a few continuous variables and automatically gives you key stats like the mean, median, standard deviation, and range, along with missing values and proportions. This is the kind of summary you'd usually have to build manually, and it's very time-consuming, but this is done instantly and formatted cleanly in one step. Now we do the same by passing in the categorical columns. So if you want to see everything in one fell swoop in one report, you can have that. And here we turn on value counts true. So this adds categorical breakdowns directly into the same table. Along with continuous summaries, we also see proportions for variables like sex, race, work class. This is a quick way to get both numeric and categorical summaries side by side without having to rewrite separate code for each. Here, we're showing how Generate Table 1 can also handle statistical testing automatically. In this example, we're grouping by income, and the function runs the chi-square test for each categorical variable to check for any significant differences between the income groups. And you can see those results on the right where the p-values are listed next to each variable, and that means we're not just summarizing data anymore, we're adding statistical context to it. And from a code standpoint, the logic is all handled inside the same call. Group by call equals income. You can group it by whichever column you want. And this triggers the tests. and the output includes everything in one clean markdown ready table. So now that we've got our baseline summaries from Generate Table 1, the next natural step in the pipeline, in the EDA exploration pipeline, is to start comparing groups. That's where this stacked crosstab plot comes into play. Instead of just looking at averages or counts, this one lets us visualize how categories relate to each other, like gender by age group or income by education. So what we do here is we take what would normally be a bunch of manual crosstabs and plotting code and turn it into a clean, reusable call. So it looks like this. Here we use the stack crosstab plot function from our EDA toolkit. And on the left, we define 3 key lists that drive the loop logic. The func call is a list that specifies which categorical variables we're analyzing. In this case, sex and income. Legend labels is a list that defines the labels that appear in the legend for each variable. And this holds the corresponding plot titles where you see title equals in that list of sex and income. And on the right, we call the function itself. We pass in the data frame. We specify the age group. That's the main column of interest, and then loop through each variable in that list function calls. So the variable returned at the bottom, crosstab age sex, represents the separate output for each plot. So not only are you going to see plots, you can also retrieve the data frame with the numeric representations. That's what the return dict equals true flag allows us to do, is to access the plots programmatically so we can easily extract and reuse them later in the workflow. Each plot shows the age group distribution stacked by either sex or income using consistent colors and formatting. You can change them up as you see fit. The top shows the raw counts of males and females across age groups, while the bottom chart normalizes them by percentages and highlights their relative prevalence rather than the population size. This is the table that summarizes the data numerically. It shows the count, the percentage of males and females in each age group. You can see the female proportion increases steadily with age, reaching around 70% in the middle and older age brackets. So that matches what we saw earlier in the stacked plots. This displays the underlying crosstab in the notebook and shows the same count and percentages that we saw in the plots. So once we've looked at categorical relationships, the next step is to understand how numerical features relate to each other. That's where this flex core matrix comes into play. Instead of running separate correlation calculations and doing things manually, building a heat map manually, this function does it all in one shot. It builds the table, plots it, and tweaks the look instantly, as you'll see here. Just a quick overview. Each cell represents the correlation strength between 2 numerical variables in the US Census dataset. Here, the values are mostly weakly correlated. We do see a modest positive relationship between education level and hours worked per week. And the code on the right demonstrates how easily we can generate this heat map, customize the titles, labels, and color scale. Then we can simply change the Boolean to true for the triangular option, and that displays only 1/2 of the heat map versus the entire thing. And this removes redundant information if you need to do this for your paper, for example. And doing this manually is a bit of a pain repetitively. So now that we've explored relationships between variables, the next step is to look at how each variable behaves on its own. That's where the KDE distributions comes in. We start simple. We have a histogram. We want to see the overall shape of the data. We use the KDE distributions with plot type equals hist. That's the input parameter. And vars of interest equals age. So we get this clean view of how age is distributed. Most people fall between 20 and 50, and the drop-off after that shows a clear right skew. So this gives us a quick baseline before we layer in more detail, like density curves or subgroup comparisons. There's that kernel density estimate. We get that by specifying plot type equals both. So that allows you to see both the histogram and the kernel density estimate. When you add plot mean equals true, you get that blue line for the mean. And this dashed line gives us a clearer picture of the data's central tendency, overall distribution shape, and combines the visual density and numerical context in one step. Similarly, we can add plot median equals true, and now you see both the mean and the median. You can plot one or the other or none. It's up to you. It's fully customizable. Next, we can also customize whether we have 1, 2, or 3 standard deviations to be displayed. And that's that. So far we've looked at individual variables and pairwise relationships, but if you want to go broader, to see every possible combination of features in one go without manually looping or writing custom summaries each time, that's pretty much why we did this. We wanted to summarize all combinations to pick your variables, run it once, and automatically create all the different summary tables, format them, and export everything out straight to Excel. Because you never know when you need to work with Excel and have everything ready in that format to send over to somebody else. Some people find it easier, to each their own. So what this does is we include the data frame inside summarize all combinations. We list the unique variables that we wish to compare. If you want to output it to Excel, you include the output path, and voila, there's what we end up with right here. And you see some of that printed below. But in Excel, as you can see, when we export and pop it back open, everything's fully automated. It even builds a clickable table of contents. So each tab takes you straight to a different variable combination. Every sheet includes counts, proportions. So basically gives you a full exploratory map of your data set, and it's ready to navigate without writing a single extra line of code. And so now that we've uncovered summaries and distributions, let's shift gears a bit to relationships. Because once you know how your variables behave individually, the next step is seeing how they interact. I mean, sure, you can have your standard run-of-the-mill scatter plots. Why not? But here, the scatter fit plot function gives you control over what's displayed. In this first example, we enable add best fit line equals true and show correlation equals true. So each subplot includes a red regression line, the line equation in the legend, and the correlation value in the title. In the second example, we turn those off and instead introduce categorical hue using income levels. Pretty standard stuff so far, but this not only highlights how the same function can instantly switch from analytical mode to comparative visualization, it shows how hours worked varies across different income groups. And last but not least on this piece is we want to build from what we've already shown. And so in this example, we take the idea even further by summarizing all numerical combinations in the data set. Instead of manually specifying pairs, we use df.select dtypes, np.number.columns to list. So we get all the numeric data types and we pass that in. We get an automatic generation of every possible numeric pairing, because sometimes you just don't know what numeric relationships you need to plot, so why not plot them all? And so that's what this would look like in full with respect to this data set. And now I'm going to pass it over to my colleague Oscar to introduce Data Doctor.
Thank you, Leon. Okay, so next we're going to look at the Data Doctor function. And the Data Doctor function consolidates repetitive EDA steps, such as analysis, transformation of a feature, visualization, and optional write back to the data frame itself. Excuse me. And this works for any numeric feature in the data frame. So what does Data Doctor do in one go? It profiles a feature. First thing it does, it looks at one numeric feature in the data frame, provides a summary of min, max, mean, median, standard deviation, quartiles, IQR, and also the 1.5 times IQR outlier bounds. So that may sound very much like the pandas described, which it is in certain ways, except that it's also providing us some of that IQR outlier bound information. Number two, it plots the same way every time. So as you'll see right now, Data Doctor produces a plot, the same plot every time. It's a KDE, a histogram, and a box byline plot, and it's in a consistent layout. And some of the magic that starts to happen in Data Doctor is that we're able to tell it to scale the data. We can tell it to transform the data to one of several scalar options, such as log, min-max, standardized, robust, and several others. And finally, it writes back to the data frame so that we have the original raw feature and also the transformed versions of that same feature. So let's look at this demo. We're going to look at one feature, which is the age column from the UCI Census Income data set. We're going to run it through the Data Doctor and show how it profiles, plots, and transforms a single feature. Okay, so let's start with the raw age. At the top, as you can see, we're running Data Doctor. Our data frame here is X, and the feature name is age. So this here is our raw profile of age, the way it's reflected in the data set itself. The next thing we're going to do here is we're going to apply transformation. So as you can see there at the top, we've added a flag of scale conversion equal to log and apply as new column to data frame equal to true. So as you can see, well, first, let me go back a slide. You can see our shape of our raw data, some outliers there on the box plot. But once we've applied that log transformation, those visuals are showing us that now we have more of a normal curve there in the KDE. The box plot itself took care of those outliers. And since we are doing apply as new column to DF true, we get a new column indicator here. So our new column that's been added to that same data frame is named age log in this particular case. Next, we're going to do a different scalar. We're going to do min-max. And so here, it retains the same shape of the original feature itself. However, the advantage here on the min-max, as you can see at the very bottom, it gives a low cutoff of 0 and an upper cutoff of 1. And we also have outliers, which is very important to observe right here. And let me draw your attention to the histogram plot. The very far right of that histogram plot has a very small spike. That's important in our next slide. And again, we applied the flag apply as new column to df true, and so we're going to get a new column out of this named h min max. Now, before I go to the next slide, let's look at that outlier bound in the data summary, Data Doctor summary report. Our upper bound is at 0.8356. So let's just make a mental note of that because we're going to use it on the next slide. Okay. So I'm calling my new feature that was created in the previous slide. I'm applying a new flag, upper cutoff equal to 0.8356, and also the flag apply cutoff equal to true, and the same flag we've been seeing to write this back to the data frame. That creates a new column name for us, h min max with cutoff, and as you can see now in the box plot, those outliers got compressed, which is also visible now in the histogram, very a taller spike versus the previous slide. And that's exactly the outcome we want for the calls that we did in the flags. So now that we've got all four versions of age, the raw one, the log scale, the min-max, and the cutoff version, we're now going to compare them side by side. So on the plot on the left-hand side are the original scales. And as you can see, our original age has quite the range there, while all of our other transformed versions are compressed a lot closer to 0. However, when we compare them under a normalized status, we can see that their means are all within 0, which tells us that they all retained their data signal. It wasn't distorted by these transformations, so that's actually really good. And one quick note, this box plot here is not something that EDA Toolkit it's something I created separately just to show possible next steps after using the Data Doctor tool for further analysis. Okay, so here we have a heat map of sorts. But before we read this heat map, I just want to give a quick heads up. This is not the standard Pearson correlation matrix. Normally, a Pearson correlation matrix shows how every feature relates to other features. In this case, what I did is on our y-axis, we have all of the other numeric features in the data frame. And then in our x-axis, we have our raw age, the log version, the min-max, and that min-max cutoff. And these are all reflecting normalized equivalents. So when we see 0.96, for example, that doesn't mean it's a 0.96 correlation. It's just relative in terms of a percentage. So really what we're looking to get out of this is which of our transformations has better signal with each of these y-axis features. As you can see here, the log version won in many of these rows, except for the final weight feature. So this is really helpful in terms of comparing transformations versus the remainder of the features. So this last slide here just shows a quick animation that cycles through some of the plotting options inside of Data Doctor. You can focus on just one of the 3 plot types, for example. Say you only want to see the KDE or only the box plot instead of the full layout with those 3 plots. You can see as it cycles through this animated image, you can change those flags to do that. And so the flexibility of this tool is consistent, and so are the visuals, and that's what makes Data Doctor feel like a complete tool. It's not just automating steps, it gives users control without complexity. So that's where Data Doctor ends. It's a consistent, extensible, and customizable tool. So in conclusion, the functions that we shared today are just a few highlights from the EDA Toolkit. We designed them to make exploratory data analysis faster, more visual, more consistent, the kind of tools we wish we had when we first started every project back during our master's program. But there's more in the library. We encourage everyone here to go import the EDA Toolkit, play with it, and because at the end of the day, the goal of the EDA Toolkit is simple. It's make exploitation reproducible, shareable, and open.
And before we get into our thank yous, I also want to add that EDA is not a one-size-fits-all solution for everybody. It's not a very quantitative process, although it can be at times because it's blended with pre-processing, and sometimes those areas are blended and murky. But like my colleague Oscar said, we invite all of you to visit our GitHub repo and pip install EDA_toolkit, play around with it, and submit a pull request. But yeah, we want to thank Dr. Ibrahim Tarshizi. He's the academic director of the Master's of Science in Applied Data Science program at the University of San Diego, where we completed our master's several years ago. And you know, that's where we first met, and that's where this collaboration really started. And you know, we just want to also take the time to thank our home institutions, UCLA Health and the University of California, Riverside. They've supported our applied data science work that connects analytics, research, and real operations. And of course, a big thank you to JupyterCon for the opportunity to share this work, for creating a space where open source tools like this can reach people across organizations and disciplines. Thank you.
Thank you.